So, hello again. Welcome to the fourth lecture on the series of lectures on Hilbert-Schmidt operators. And today we are going to see uh, that norm t or minus norm t is an eigenvalue of a compact self-adjoint operator. So, if we recall what we have seen in the previous lecture, in the first lecture we have seen definition of Hilbert-Smith operator and some examples. In the second lecture we have seen a Hilbert-Smith operator is compact. So set of all Hilbert-Smith operator is a subset of set of all compact operators. Not only that, it was an exercise that it is a subspace in fact. And in the third lecture, we have seen that a Hilbert-Smith operator T, then its adjoint T star, that is also Hilbert-Smith. And then in the definition of Hilbert-Smith operator, uh, the the condition summation n equals to 1 to infinity norm of tu n square is convergent. That does not depend on the orthonormal basis un. One can take any basis, and by from that condition we defined a norm, and that was left as exercise to verify that in fact it is a norm linear space. And probably this is the final lecture because already I posted one lecture on YouTube before uh, during the lockdown. So before we see this result, let us consider one example, that if we consider an infinite matrix of a Hilbert-Smith operator, what is the condition based on the coefficient of the matrices? So let us consider this example first. So suppose we have H equals to L2 and T belongs to BLH. So suppose T is given by the matrix. So let us call matrix of T equals to alpha ij. Right, so this is infinite matrix I and j. Uh, they are natural numbers 1, 2, and so on. So that is matrix of T will look like this. We'll have alpha 1 1, alpha 1 2, alpha 1 3, and so on. Alpha 2 1, alpha 2 2, alpha 2 3, and so on. Alpha 3 1, alpha 3 2, alpha 3 3, and so on. And this is in BLL2. So it is an infinite matrix, right? This is not finite matrix. This is an infinite matrix given by alpha ij. We know how do we write the matrix. So what is T of E1? So coefficients, when we write T of E1 in terms of orthonormal basis, standard orthonormal basis, what we get is alpha 1 1 E1 plus alpha 2 1 E2 plus alpha 3 1 E3 plus and so on. So this is nothing but summation I equals to 1 to infinity alpha I 1 EI. T of E1, these coefficients we write in the column. So here we have alpha 1 1. So we write here alpha 1 1, and then we have alpha 2 1. So we write in this column. Right. So this is how we express. So in general, what is T of EJ? T of EJ, if you want to write, this will be summation I equals to 1 to infinity alpha I, instead of 1 we have now general entry, jth entry, alpha ij ei. So this is TEIJ. And now let us check, suppose we assume that this is Hilbert-Smith. Suppose we take T to be an Hilbert-Smith operator, then what will be the condition on this coefficients? So if T is Hilbert-Smith, what we know is summation j equals to 1 to infinity norm of TEJ, if this is an orthonormal basis E1 E2 and so on, then this series is convergent. The sum is finite if it is Hilbert-Smith. But then what is this? What does this imply? Summation j equals to 1 to infinity. What is norm of TEJ square? So norm of TEJ, so when we take norm here, we'll have norm here, right? So uh, I'll write summation I equals to 1 to infinity. This should be written in norm of alpha ij ei square, right? So this is nothing but this is summation j equals to 1 to infinity. Now what about this? So if we write this, we actually, what we do is we expand this in terms of inner product. Norm square is inner product of summation alpha ij ej with itself. So summation, let us say here alpha I, sorry, here ei. So alpha, instead of I, let us take alpha kj and then ek, and then we take this inner product. So from here alpha ij will come outside, here alpha kj bar will come outside. So this just I am showing the calculation, alpha kj bar, and then ei ek. So because it is orthogonal basis, it will be 0 if I is not equals to k, and 1 if I equals to k. So only those terms will be non-vanishing when I equals to k. So when I equals to k, alpha ij bar. So that will give us mod summation I equals to 1 to infinity mod alpha ij square. So this is what we get, right? Because there are two sums here. So there is again sum I equals to 1 to infinity. Here there is sum k equals to 1 to infinity. So both sums are here, summation. But then one sum will vanish when I is not equals to k. So all those terms will be 0. So only this sum is left. So if t is Hilbert-Schmidt, this sum we know it should be this should be a finite sum. So this is the condition for an operator to be Hilbert-Schmidt is this. It's matrix. So if T is in BLL2 and it's a Hilbert-Schmidt operator with matrix, let us say alpha ij, then what is the condition? That entries of those alpha ij must satisfy this condition. I hope this is clear. If it is not clear, you can pause and or watch again. And if you have any doubt, do let me know. So this is what actually is given here. Let me show you. Yeah. So this is here I have directly given the condition first, and then I have written that T is a Hilbert-Schmidt operator. So alpha ij is a matrix of T. T is an operator on L2. So if alpha ij satisfies this condition, then we can check norm of T ij square equals to this norm square is nothing but inner product with itself, and then verify that this will give you this term. And so because it is Hilbert-Schmidt, summation j equals to 1 to infinity norm T ej square is finite. So and that gives us this condition. Because it is finite, so T is Hilbert-Schmidt operator. On the other hand, if we assume T is Hilbert-Schmidt operator, we get this is the required condition based on the matrix. Right? So this example is covered. And now this result, this is already I have made a video in on my another YouTube channel before when there was lockdown. If you remember, I sent you a video. So what it says that H is Hilbert space and T is compact. If T is compact, then every non-zero, every result is this. I have written in symbols. Every non-zero approximate eigenvalue of T is also an eigenvalue of T. Is also an eigenvalue of T. This is very useful result. We'll see in the next result how it is used. So what it says, if T is just compact, if we assume this compact condition, then every non-zero approximate eigenvalue of T is also an eigenvalue of T. Now you recall what is the relation between eigenvalue and approximate eigenvalue? We know in general sigma ET is subset of sigma AT. right? So every eigenvalue of t is also an approximate eigenvalue of t, and we can remove 0. Suppose if I remove 0 from this, then I can write, anyway it is subset of sigma 80, but if I want to write, I can write like this. So this side is anyway true in general, but what it says, if t is compact, then every non-zero approximate eigenvalue of t is also an eigenvalue. So this is set of all 0 is removed. So this is set of all non-zero approximate eigenvalue. It says that it is also an eigenvalue of t. So what it says that this is subset of this if t is compact. This is what the result says. Yeah, so if t is compact, then every non-zero approximate eigenvalue is also an eigenvalue of t. So in fact, we have equality here. This is anyway true in general, and so we have equality. Right, so this was the statement, and we are going to use this. I've already made a video of this. I'll give you the link in my other YouTube channel. You probably have it in the WhatsApp group also. So we use this result to prove our main result, what we stated earlier, which was this. So if t is compact self-adjoint operator, then norm t or minus of norm t is an eigenvalue of t. So what is given? T is a compact self-adjoint operator, then either of this is an eigenvalue of t. So we don't have to prove eigenvalue because of the compact condition. What we can show is compact. We can, instead of showing eigenvalue, we can show it is an approximate eigenvalue also, right? So let us go to that result. Yeah, so this is the result which I was talking. So T is Hilbert, H is Hilbert space, and T belongs to BLH, and it is compact self-adjoint. Then what we have to show, either norm T is an eigenvalue of T, or minus of norm T is an eigenvalue of T. Uh, because it is compact, by the previous result, what we have is sigma Et minus 0 equals to sigma At minus 0. So instead of proving eigenvalue, what we can prove, that it is, instead of showing it is in sigma Et, we can show that it is in sigma At because it is compact. So by previous result which we just stated, right? And now this is self-adjoint also. So by this result, what we have due to self-adjoint. So if it is self-adjoint, what we know is, so this result we know, right? If it is self-adjoint, then suppose T is self-adjoint, then norm T is, this is a corollary of, you might have to recall, if it is self-adjoint, then this is subset of R. Numerical range is a subset of R. Capital MT was supremum of WT, and small mt was infimum of numerical range. And these two things to remember, right? That norm T is maximum of mod of MT and capital MT, and this both, infimum of numerical range and supremum of numerical range, both belong to the approximate eigenspectrum. So just remember this. You have the notes, you can keep it open and refer it to that. What we are going to use is this. So we now go back again to our result, which was, yes. So we come back again here. So because T is self-adjoint, what we have, because T is self-adjoint, we have this. Both the bounds, infimum and supremum of numerical range, both are in sigma At, approximate eigenspectrum. And also we have norm T equals to, by this corollary, norm T equals to maximum of modulus of this T. So now we have two cases. What we have to show, we have to show either this or minus of that norm T is in sigma At, then we are done. Because it is compact, sigma At is equals to sigma At by this by the previous result, right? So this is the first case. What is the first case? That sum of this is greater than 0. And the second case, that sum of this is less than 0. So if sum of this is greater than 0 and the small mt is infimum, so what we know is small mt is less than or equals to capital MT. So when their sum is greater than 0, both cannot be negative. Why both cannot be negative? Let me show you by drawing a picture on real line. Right? Suppose this is 0. If both are negative, of course this is infimum, so MT is less than equals to capital MT. So suppose MT is here somewhere, so this is negative, capital MT is also here, so both are negative, the sum is also negative, so it comes in this case, so which is not the case. So uh, both cannot be negative, and if both are positive then it is okay. So suppose both are positive, so we know capital MT is here, small mt is less than or equals to that, so both are positive. So when we take modulus, which one is greater? So modulus, when we take, we know of course this capital MT is, this is mod of capital MT, distance from origin, this is greater than mod of small mt, right? So in this case this is greater, and we have to consider another case when one is negative and one is positive. So 0, suppose this is positive, and suppose small mt is negative, so where it can be? It can be somewhere here. It cannot be more than, the distance cannot be more than this distance. For example, suppose this is 5, this is minus 2. What is addition? Addition is 3, which is positive, which we know it is greater than equals to 0. That is our case. So small mt can be up to here only, where the value is, let us say, minus 5. Then the addition will be 0. 0 is allowed because there is equality. But small mt cannot be here. Small mt, if it is say minus 6, so then the addition is negative, which is not the case. So small mt cannot be here. So uh, very small mt, it, we have to take care of the distance, and distance is distance of small mt is this, and it must be smaller than this, right? So I hope this makes sense, because the addition is greater than 0. Of course if capital MT itself is negative, then both are negative, which is not the case. If both are positive, this is anyway less than that, so capital MT will be greater than MT in this case. But suppose this is positive and this is negative, but because their sum is positive, so this distance cannot be more than this distance. So what about this? This is mod of MT. Anyway, MT is positive, so mod MT or MT, it is one and the same thing, and it is obviously greater than this distance, which is mod MT. So in this case, mod of so MT is great, capital MT is greater than supremum of numerical range is greater than absolute value of infimum of numerical range. So in that case, what is norm t, maximum of this? The maximum will be this. It belongs to sigma at. Right. Second case, the sum is negative. Sum is negative. What are the possibilities? So sum is negative. Then let me, yeah, sum is negative. So it can happen both are negative, capital MT and small mt. If both are negative, then what is the modulus? Which one is maximum? Obviously, this is maximum. So modulus of small mt in that case is greater than modulus of capital MT. Another case, one is positive, one is negative. Both cannot be positive. So what is positive? So MT is positive, and this one is here, MT. But remember, their sum must be less than 0. When is the sum less than 0? When this distance is more than this distance. Right? For example, let us say this is minus 4, this is 2, then the sum is negative. So this distance has to be more. So in that case also, mod of MT is greater than capital MT. So in that case, maximum will be this one. So maximum is norm t. So but that is mod of mt is norm t. So what will be mt? We know this 2 belongs to this. What will be mt? Mt is negative. Mt has to be negative, otherwise the sum cannot be negative. So small mt has to be negative. So in that case, mt will be nothing but, if because it is negative, when we remove the modular sign, it will be minus norm t, and that belongs to sigma at. And so either this or this belongs to sigma at. If it is non-zero, then because it is compact by the previous theorem, it is in sigma et minus 0. So that means it is a non-zero eigenvalue of t, right? I hope I have explained this in a better way and not confuse you more. If there is still confusion, I think I can try better than this. So do let me know if you need another video explaining these cases. But I think if you try on your own, taking some examples like this, then you will understand it's just logic. Nothing it has to do with this. Just consider these two cases, and it will have two sub cases. Do let me know if you need any further explanation in this. Okay, so let me consider now. So this will finish our revision part. Only thing is the spectral theorem on complex self-adjoint operators. So this is statement only. You can read it. It might be asked for 2 marks question. Right. So this finished the revision part. Provided that you see the video of this. Already I have made a video of this earlier. And if you need any more revision then on function analysis, then do let me know. Okay. Thank you.